Right, okay, so on the test, you're going to be asked to demonstrate your knowledge of Dijkstra, A star, adding and removing nodes from a tree, and also post-order traversal of a tree. Okay, so they're all pretty standard. The one that's a little bit complicated that you've got to do is depth and breadth traversal of a graph. Okay, when we're looking at trees, it's easy to infer order because you can say like left and right and things, but with a graph there is no order. So let's just have a look at how we do this. Now, I don't know, it doesn't matter what I do. So I'll just do this little, I'll just knock up a little graph. I'll circle all the nodes first, it's probably easier. Right, the nice thing about the depth and breadth searching is essentially the algorithm's the same. The only thing that changes is the data structure. You use a stack or a queue. Okay, so the process is the same. Okay, so that's just a little graph. Now, the problem you've got when you look at a graph, you can't... oh dear. It's impossible to say what order that you visit your neighbours, or you look at, or you examine your neighbours. So if we look at node A, so we're going to do a search on this graph from node A. You can't like say to the left of A and do it, go left to right and order the nodes F, B. So you can't do that. So what I'm asking you specifically to do in the test is to use alphabetical ordering. All right. So let's do a breadth search of this. Now, if you want to do it diagrammatically, the breadth search, that's fine. But I'm going to show you how to use a queue, because that's what breadth search does. Okay? The process is ridiculously simple. The first thing is to on-queue our start node. So I'm going to do it from A. Oh God, I've got to spell on queue now. So I'm going to on-queue A. So all I need to do is make myself a little queue. So I'm going to do that down here. The queue one is easier to do than the stack because the queue just grows, doesn't it? So, right, so I start like that. And then the process is just to take things out of the queue, add neighbours that we haven't visited, and then just keep doing that until the queue's empty. Okay, so step 2 is just to dequeue, write down what we got, and when I say write down, we're basically saying we've visited that element. So I'm gonna make a little visited, and that is the order that I've visited the nodes, which is what you'll be asked to demonstrate, obviously. So I've got A down. So what I now do, and I've got my queue there, and just to help me and double check myself, I'm going to just put an X to say, right, well that's gone. That's not in the queue anymore. Now I'm going to look at my neighbours. And I'm looking at neighbours that I have not visited. If I don't do this, I will end up going round and round the graph forever. Keep adding on neighbours. And sometimes you actually want that sort of behaviour, but in general we don't. We just want to visit the nodes once. So this is a general search algorithm really for an unknown graph. When you're just looking for a node but you don't even know where it is. Okay. Right, so I'm looking at my neighbours. I've got neighbours that are connected to A are F, G, K and B. So the order that we need to process them will affect the order that we visit nodes. So we're going to do it alphabetically. So I'm going to on-queue alphabetically. So I'm going to on-queue all the neighbours. only if they haven't been visited. And I have said it twice on the test, and I've actually given you an example of what I mean, so that you will not, please don't screw that up. All right. So I'm just going to add them alphabetically. So, assuming that you all know the alphabet, which sometimes is a big ask. So B goes on first, then F, then G, then K. Okay. So I've just added to the queue. Right, so step 4, if the queue empty, stop. When the queue isn't empty, and then if that's not true, we just go back up and do a DQ again. And that's it. So the search can examine a massively complex data structure, but the actual steps are relatively simple. So I'm going to DQ the next thing. Obviously, I'm assuming you understand how a queue works. We remove from the front, we add at the end. Right, so B is now marked as visited, and we look at the neighbours. It's got 2 neighbours, A and D. A's already been visited, so we're going to ignore that. But D's a new one, so we're going to add D to the queue. There's only one, so we didn't have to get into any alphabetical shenanigans. Right, okay, we've still got stuff in the queue, so we're going to DQ again. Write it down. F has only one neighbour, A, which we've already visited, so we've got nothing to add. So we just go back round and DQ. G has no neighbours other than A, so it's just a matter of writing it down. Let's DQ again. K's got a neighbour, A and C. A we've seen before, C we haven't, so we add C. Go back round, DQ. D comes out. Right, I've made a mistake. What mistake have I made? No. No. Worse than that. I haven't written. I didn't mark K as visited. I've taken it from the queue, but I didn't write it down. So I'll be very careful. I hate that. God. That's so obtrusive. Right. The reason I write my queue out like this is because I can double check. Alright? So I can say, alright, G, I did K there, I didn't write K down. Always try and get into the habit of taking it out, write it down. Right, okay, so we did D. Okay, so we've written D down. It's got no neighbours other than B. We already visited B, so we don't need to add that. Right, remove the next thing from the queue. The queue's actually at a point where it's empty, so this could be the end, but it's got 2 neighbours as C. So I'm writing C down. A neighbour K, but we've already visited K, but it has actually got this new neighbour L. So I'm going to add L to the queue. I'm then going to go back round, DQ, so take the L. L has only got one neighbour C, which we've already visited, so there is nothing to add. So we now look to take something from the queue, but the queue is empty, so we've finished. Okay, so the only thing that you've got to remember is make sure you add them alphabetically to the queue, where you have got more than one neighbour to add. Okay, right, let's do the exact same thing now, but do a depth search. So if we do a depth first search, same graph, I'll start at A again, but this time we use a stack. So I'll just put the graph in the corner out of the way because I'm going to put my stack up here. Right, the problem with using stacks is they can get messy. You do not want to do this. You don't want to, like, say, add some stuff to a stack, start removing things from a stack, add some more things to a stack, remove some stuff from a stack. You don't want to do that, because that will lead to a real cock-up. You'll miss something in the stack. So the best way of tackling the stack, adding and removing, is whenever you pop, redraw the stack. So you keep a clean copy. If you're pushing things on the stack, it doesn't matter, just keep pushing. But it's when you do a pop. That will also give you an added benefit of giving you the order that you pop things, because you'll have a pop every time. So let's go through and do a depth first search, or depth first traversal. What's the difference between traversal and search? Yes?
Traversal goes through all nodes while the search looks for a particular one.
Yeah. Traversal will visit all nodes. Search will use the same algorithm, but it will stop if it finds a target node. If the node doesn't exist, then it will do a traversal. Okay? Right, okay, so I'm going to draw myself a little stack. Yeah.
The search will finish when it marks it as visited.
Yeah, not when it sees it as a neighbour.
Not when it adds it to the queue.
Yeah.
When it visits.
Yeah, when it marks as visited. It's when we actually pull it from the queue or the stack. Right, okay, so we're going to start at A. So just like in the depth algorithm, the first thing we do is we push our start. So we're going to push our start node, A. And the algorithm is exactly the same. Instead of dequeuing, we're popping. All right, so we're going to pop A. So we show that by going like that. And we can cross it out as well if we want. And I'm going to redraw my queue. And I'm going to write down what I popped. So that again is my visited list.
You're required to show that in the test.
I want to know you're going to get your marks for the order that you visited. How you manage to work out the order that you visited is up to you. Okay, if you want to, I'm not going to give you marks for showing the stack, because that's the method but not a requirement. The requirement for me is that you visited them correctly, because your visited list is in the right order. Okay, right, so we've popped A. We now need to push the neighbours, but we're doing it alphabetically. So B gets pushed first, then F, then G, then K. So this does alter the way which we process this graph. All right, so I'm pushing them alphabetically. So that's the end of the loop process. I'm just going to go around and pop the next thing. So I'm going to pop off a K. Write it down. So if I screw up, I can go back to my stacks and see the values I popped. All right, so I can use that as like a double check for myself. So I'm going to redraw the stack with just the current contents. So it stops at G currently. Right, so I've popped K. I'm looking at my neighbours. A I've visited, the other neighbour is C, so I'm going to push C onto the stack. No more neighbours, so I'm going to go back round the loop and pop. So you can see, as the nature of a stack, the last thing we put on is the thing that we process first. So C gets popped. Looking at the neighbours of C, we've got K, but we visited K. But we have got another neighbour, L. So I'm redrawing my stack. So it's got B, F, and G on it. C came off, but L's going on the top. I've finished dealing with neighbours. So I am going to now pop. So I pop the L and I look for the neighbours of L. It's only got a neighbour C, which we've already visited. So the stack ends up like that. Pop again. So I'm now going to pop G. Write it down. Neighbours, the only neighbour is A. So there is nothing to add because that's already been visited. Okay, go back round, pop again. So I'm going to pop F. Redraw my stack. F's only got a neighbour A, which we've already visited, so there is nothing to push for this value, this node. Right, so we're going to pop the stack again. The stack is empty, but we haven't finished processing B yet. So, looking at the neighbours of B, it's got a neighbour A, which we visited, but it has actually got this new neighbour D. So when I redraw my stack and it's empty, I can push the D on. I'm then going to write it down, and I look at my neighbours. B is my only neighbour, so there's nothing to push. My stack is now empty and the algorithm finishes. So the answer that we're looking for, the order that we visit the nodes, assuming we push alphabetically, is A, K, C, L, G, F, B, D. And you can see from looking at this that we have gone, just in the nature of the way that the alphabetical ordering worked, we've followed the full extent of the A, K, C, L path through the graph first before we examine the other ones. And that's the nature of depth first. You will get to an extent before you come back and backtrack. Okay, whereas the depth one is a layering effect, isn't it? So you would use a depth search if you were doing some sort of game set of rules or game moves, and you wanted to like say, what potential positions could I get to in 3 moves? Then a depth first search would allow you to examine those 3 moves on positions. A depth search would allow you to find out what an end solution was for a particular direction through a decision graph. Okay? Okay, I'll stop that recording there and I'll upload that.